Hi, I'm Jamie Watson from Niantic's R&D. I'm excited to tell you about learning stereo from single images, a new approach to training deep stereo matching networks. We build on recent advances in monocular depth estimation and show that it is possible to use any collection of single images to train accurate stereo networks. Given a pair of input images, the aim of dense stereo vision is to estimate the relative disparity by solving a per-pixel correspondence problem. That is, we wish to find the horizontal displacement of a pixel between a left and a right rectified image. The disparity can subsequently be converted to depth given a known baseline and focal length. Recent state-of-the-art results are achieved using deep stereo networks and ground truth supervision. Such data consists of a stereo image pair and ground truth depth aligned to one of the images. Unfortunately, accurate per-pixel correspondence data collected in varied scenes is very challenging to acquire, involving not only calibrated cameras, but also expensive depth-sensing hardware and high-quality synchronization. As a workaround, the community has largely relied on using synthetic data such as the scene flow dataset to train deep stereo networks. So, it is a standard practice to pre-train stereo networks on large amounts of synthetic data and then fine-tune with the available small quantities of real-world data. However, here we focus on the case in which there is no real-world stereo data available to fine-tune. At first glance, we may have to rely on a purely synthetically trained network. Unfortunately, models trained on these synthetic datasets alone still have problems generalizing to real scenes due to the large difference in appearance statistics. In this work, we show that it is possible to train accurate stereo networks without requiring any synthetic or real-world ground truth correspondence data. By taking advantage of recent progress in monocular depth estimation and with a carefully designed depth and image synthesis pipeline, we can convert any monocular image collection, such as the COCO dataset, into effective stereo training data. Here we note the related work single-view stereo matching, which makes use of image synthesis and the training of a stereo network to improve monocular depth estimation. In contrast to their approach, however, our goal is generalizable stereo, and we require no synthetic data or even stereo pairs of images to train. This is achieved by using a monocular depth network to estimate a depth map for each image, which we convert to disparity, and use to synthesize a plausible corresponding image for the stereo pair. We now have everything required to train deep stereo networks, the two input images and a ground truth target disparity, importantly, all of which are geometrically consistent. We note here that perfect depth prediction from our monocular network is in fact not required. It needs only be plausible, as the network is being trained to perform pixel matching. To go into more detail about our image synthesis, we begin with a disparity map and a single image, which we always treat as coming from the imagined left camera. If our disparity was aligned with our right image, we could use backwards warping, where we grab pixels from the left image. However, since our disparity map is aligned to the left image, we must instead use forward warping, whereby each pixel is pushed into the synthesized image, being shifted d pixels to the left. Our disparities are non-integer, and so we use interpolation to arrive at our final right image. Here we can see an example result. Forward warping brings about additional challenges due to occlusions. These are collisions and holes in the synthesized images. Collisions occur when multiple pixels in our left image map to the same location in our right image. When these occur, we select the pixel with the highest disparity value, as these are closer to the camera and thus should be visible in both views. In practice, we identify pixels in our disparity map which land behind another pixel after warping and mask them out during our image synthesis. Additionally, holes appear in our synthesized image when no pixels in the left image map to a location in the right image. Luckily, the network never makes a prediction for these pixels. However, to improve the realism of the stereo pair, we address them in two ways. First, we always crop the right-hand side of the synthesized image to remove large regions of missing pixels. Second, we select a random image from our training set to act as the background and perform color transfer to more closely align the image statistics. We then use this to fill in the remaining holes. We also propose a pre-processing step for our disparity maps to help improve the resulting synthesized images. A typical problem with monocular depth networks is that they often blur edges around depth discontinuities. Naively warping using these disparities will result in flying pixels, where individual pixels are warped to empty regions between two depth surfaces. Not correcting this problem would result in a collection of synthesized training images where the stereo matching algorithm is expected to match pixels in the left image to individual isolated pixels in the right image, which is a highly unrealistic test time scenario. We address this by performing depth sharpening. That is, we identify flying pixels in the disparity map as those with a Sobel edge filter response greater than a threshold, and set their values to the nearest non-flying pixel in image space. As you can see, this simple pre-processing step effectively removes flying pixels in our final synthesized images. Here, we see some example synthesized images from the COCO dataset for a range of maximum disparity values. Of course, we could make use of more sophisticated depth-based rendering techniques and hole-filling algorithms. However, we found our simple approach to be fast and effective, and also easily allows for data augmentation at training time. To demonstrate the effectiveness of our method, we perform a series of experiments to compare it to existing deep stereo training pipelines. Unless otherwise stated, we use PSMNet as our stereo network and MIDAS to generate monocular depth. In general, we consider our baseline to be a scene flow trained network. We collate a dataset called Mono for Stereo, or MFS, which consists of single images for use as input to our stereo image synthesis approach. MFS consists of almost 600,000 images, giving a large variety of scenes under diverse imaging conditions. We evaluate our performance on the following 4 datasets: ETH3D, which consists of 21 grayscale images covering both indoor and outdoor scenes; Middlebury, a dataset of 15 high-resolution indoor complex scenes; and the Kitty 2012 and 2015 stereo dataset, which consist of images taken from a car along with ground truth provided by LiDAR. In our first experiment, we show that stereo networks trained with our approach outperform those trained with synthetic data across a range of benchmarks. Here, the green bars indicate percentage improvement over scene flow of our approach trained with a subset of images from our MFS dataset. As we add more images from MFS during training, we observe that our networks keep getting better. The MIDAS monocular network in the previous experiments make use of synthetic optical flow data during its training. A natural question, then, is to ask if our performance gains can be attributed to distilling this supervision. To answer this, we investigate using different monocular networks trained with various forms of supervision, where each is used to generate stereo pairs using our MFS dataset. We can see that our approach still outperforms synthetic data, irrespective of the type of data used to train the underlying monocular network, whether it be 3D movies, structure from motion, monocular video, or human annotations. Importantly, we are not limited by the quality of the underlying monocular network that is used. Here we show monocular predictions for 2 Kitty images from MIDAS and Megadepth. Whilst they are reasonable, they both contain artifacts and tend to miss thin objects. In comparison, a stereo network trained with our approach is able to recover much more detail, showing that despite using inaccurate monocular depth data as input, we can still recover from its limitations. It is worth noting that none of these approaches have seen images from the Kitty dataset during their training. In this next experiment, we investigate what impact the quality of the monocular depth has on the test time stereo performance. To answer this question, we replace the deep monocular network in our pipeline with different approaches for generating weak depth cues. We use the same stereo network and underlying MFS data, only changing how we generate the depth for synthesizing the right image during training. Note that in this case, lower scores are better. First, we show affine warps, a simple approach where we synthesize a right image by applying a planar warp to the input image. Next, consider random shapes, where a background disparity is given by an affine warp, and additionally, we add in random shapes with textures taken from a different training image. We also show random superpixels, where we assume a background disparity plane and randomly select superpixels in the image to act as foreground objects, which are assigned a random disparity. Although the resulting images are highly unrealistic, the benchmark results are fairly strong. Next, we see the results of our usual scene flow baseline. Lastly, we consider a baseline from single view stereo matching, where we still use depth from a monocular network, but replace our synthesis pipeline with the selection module described in the paper. In all cases, our method making use of monocular depth has the best performance. In the paper, we show additional results where we compare several different stereo network architectures and also an ablation of the different components of our approach. In summary, we presented a new approach for generating stereo training data from single image collections by leveraging recent advances in monocular depth estimation. We showed that this enables us to train deep stereo networks that outperform those trained on supervised synthetic data. Code and data are available from our website. Thank you for watching.